Hello, this is Richard Hammack's Calculus 1 course. We are in part 2 of the course on limits. Today, lecture 9, evaluating limits via algebraic simplifications. In lecture 8, we introduced a variety of so-called limit laws that aid us in computing or evaluating various limits. However, it's a fact that for many, if not most of the limits that we encounter in this course, we'll need to first perform some algebraic simplification to the limit before any of the limit laws apply. So that's today's goal, to use algebraic simplifications to help evaluate limits. To begin, let's review our limit laws. We had 4 basic limit laws. The limit as x approaches c of x to the n equals c to the n. The limit as x approaches c of k equals k, where k is a constant. The limit as x approaches c of a to the x equals a to the c. And the limit as x approaches c of log base a of x equals log base a of c. And for this last limit law, we require that c be positive so that it can be plugged into log base a, so that it's in the domain of log base a. We had further limit laws, and for the ones on this page, the setup is as follows. Suppose that the limit as x approaches c of f of x and the limit as x approaches c of g of x both exist. Then, first of all, the limit as x approaches c of f of x, either plus or minus g of x, equals the limit as x approaches c of f of x, plus or minus the limit as x approaches c of g of x, where you use plus or minus here depending on whether you have a plus or minus here. And this has the effect of reducing what could be a more complicated limit involving a complicated sum of 2 functions as the sum of 2 simpler limits. And as we remarked last time, it's not just that you have this limit law for 2 functions, you could have it for 3 or more functions. The limit as x approaches c of f of x plus or minus g of x plus or minus h of x, for instance, equals the limit as x approaches c of f of x plus or minus the limit as x approaches c of g of x plus or minus the limit as x approaches c of h of x, and so on in the obvious fashion. We had the so-called constant multiple rule. The limit as x approaches c of k times f of x equals k times the limit as x approaches c of f of x. In other words, a constant k can be factored outside the limit. The limit as x approaches c of f of x times g of x equals the limit as x approaches c of f of x, which of course is a number, times the number which is the limit as x approaches c of g of x. The limit as x approaches c of f of x divided by g of x is the limit as x approaches c of f of x divided by the number limit as x approaches c of g of x. And it's important to note that for this limit law, it only works provided the denominator is not 0. In other words, provided the limit as x approaches c of g of x is not 0. Otherwise, you're dividing by 0, and it doesn't make sense. The limit as x approaches c of f of x to the power of n is the number limit as x approaches c of f of x raised to the power of n for any integer n. And finally, the limit as x approaches c of the nth root of f of x is the nth root of the limit as x approaches c of f of x. This limit can be brought inside the nth root. And this holds for integers n greater than 0. And also we demand that the limit as x approaches c of f of x be greater than 0 if n is even, because otherwise, if it were negative, you can't take the even root of a negative number. So these are the limit laws as introduced in our previous lecture. We had a couple of theorems that fell out of these limit laws. If f is a polynomial or a rational function, then the limit as x approaches c of f of x equals f of c for any number c in the domain of f. So in other words, if you're working out the limit of a polynomial or a rational function, the limit as x approaches c of f of x. To get an answer, you just plug in c for x. And that's nice. So a few examples. Here we have the limit as x approaches 2 of x cubed plus x squared square root of x minus 1 divided by x cubed minus 4x plus 1. And in working this out, you'll notice that we're taking the limit as x approaches 2 of the sum of two functions. So we can apply a limit law there, the very first limit law from the previous slide, to break this up in the sum of two limits, as indicated here. Furthermore, one of our basic limit laws says the limit as x approaches 2 of x cubed is 2 cubed. And then we have another limit law that says the limit of a quotient of two functions is the quotient of the limit of two functions, as indicated here. Now, looking at the bottom function, that's the limit as x approaches 2 of a polynomial. So to evaluate this limit, we just need to plug in 2 into that polynomial. And on the top, we have the limit as x approaches 2 of a product of two functions, x squared times the square root function. So applying limit laws there, we plug in 2 into the polynomial in the bottom, and on the top, we write this limit of a product of functions as a product of two limits, as indicated here. And of course, 2 cubed is 8. Now we have the limit as x approaches 2 of x squared right here, and that's going to be 2 cubed, or I'm sorry, 2 squared. And here with this limit times the radical, we have a limit law that says we can bring that limit inside the radical. So we get 8 plus 2 cubed divided by the square root of the limit as x approaches 2 of x minus 1. And this is all divided by our 2 cubed minus 4 times 2 plus 1, which is 1. And we're in a situation now where we have one more limit way inside the radical here. The limit as x goes to 2 of x minus 1. And x minus 1 is a polynomial, so we have a theorem that says we can just plug in the 2 to the polynomial. So we finally get our answer, 8 plus 4 times the square root of 2 minus 1 over 1, or 12. Now here we've worked out this example using a step-by-step process, breaking it down into limit laws, into simpler and simpler components. And you will find as you do this, you may start off using limit laws one by one, but you're quickly going to start skipping steps. For this limit, you will likely just go straight from this first step to one of these last steps and get the answer 12 immediately, and that's perfectly fine. So here we've computed this limit and got 12. You've read in your text many examples of working out limits at this point, and you've probably noticed that when we talk about computing a limit, finding its value, we often refer to that as evaluating the limit. So we have evaluated this limit and got an answer of 12. A couple of remarks. First of all, other variables than x are common. You might have, for instance, this exact same problem, but the variable is a z instead of an x. The limit as z approaches 2 of this function equals 12. And you might even skip a bunch of steps and get this answer in one step or 1 or 2 steps, which is fine, as I said earlier. The limit as h approaches 1 of 2 minus 2 over h. Here the variable is h. It's approaching 1, And in your head, you can get this answer immediately. You're probably applying limit laws in your head, and you realize, oh, well, we can just essentially plug in the h equals 1 right there to get 2 minus 2 over 1, and that's equal to 0. So again, often when it's very clear how a limit works, it's very clear that you can just apply a number of limit laws and get an answer right off the bat. We tend to do that. Though I would encourage you to write this in several steps when you first start out. We come to the most important point of today's lecture, and it concerns the limit law. The limit as x goes to c of f of x over g of x is the limit as x goes to c of f of x divided by the limit as x goes to c of g of x, which holds provided that the limit as x approaches c of g of x is not 0. You will find in this course that you will need to apply this limit law many, many, many times for important limits. And it's going to be a fact that in our most important limits, this law will fail because the limit as x approaches c of g of x equals 0. It will not apply. When this happens, your strategy will always be to try to cancel the term that makes the denominator 0. The term that was given you as 0 in the denominator. We're going to work a bunch of examples now, where in every single example, we'll cancel the term that's making the denominator 0. And in every single example, this law will fail, and we'll have to overcome it with an algebraic simplification. Let's start with the limit as x approaches 1 of x squared minus 1 divided by x minus 1. It may look familiar. We've used this limit in the past 2 lectures. In today's context, you have the limit as x approaches 1 of a quotient of 2 functions. So if you were to just blindly try to apply our limit law up here, you would get the limit as x approaches 1 of x squared minus 1 divided by the limit as x approaches 1 of x minus 1. And those two limits individually work out to 1 squared minus 1 and 1 minus 1, and we get 0 over 0. Now, 0 over 0 is not defined. It makes no sense. So this approach is wrong, and the thing that went wrong is precisely the fact that we didn't have license to apply this limit law for quotients. It only works provided the limit as x approaches c of the bottom function g of x is not 0, and here the limit as x approaches 1 of the bottom function x minus 1 is 0. So we were wrong to try to apply this limit law. So the limit law failed. Now we noted up here that when this happens, try to cancel the term that makes the denominator 0. So let's see if we can carry out that plan here. We have the limit as x approaches 1 of x squared minus 1 over x minus 1. And the idea here is try to factor before we work out the limit. The numerator factors as a difference of 2 squares, x plus 1 times x minus 1. And then the x minus 1's cancel. This cancellation happens provided that x is not equal to 1, as we discussed earlier. But x is approaching 1. It's not equal to 1. It's just getting closer and closer to 1. So these two terms are not 0 over 0. It's a quantity divided by itself, which is 1. So we're just multiplying x plus 1 times 1. And we get a cancellation. The limit in question now equals the limit as x approaches 1 of x plus 1. Now we haven't worked the limit out yet. We haven't evaluated the limit. We've just algebraically simplified. But we've arrived at a limit in which there's no denominator. We're not getting this problem of the denominator turning into 0. And in fact, this is the limit as x approaches 1 of a polynomial x plus 1. We know we can just plug in 1, and we get an answer of 1 plus 1 equals 2. So what happened in this limit where we had to use an algebraic simplification before evaluating the limit will be typical of all of our examples today. In our next example, evaluate the limit as x approaches 1 of 3x squared plus 5x minus 8 over x minus 1. Always when you're working out limits, your first impulse is to try to apply a limit law. And here you might look at this and say, well, I've got the limit as x approaches 1 of a quotient, so let me apply my limit law, and we get this limit divided by this one. And working out the top and bottom limits, we get 0 divided by 0. On top and bottom, we have the limit as x approaches 1 of a polynomial, so we can just plug in the 1 into each of these functions, getting 0 in each case. Now, clearly that's wrong. 0 over 0 doesn't make any sense. It's not defined. What went wrong? Well, we were wrong in applying the limit law in this step because it doesn't apply. The limit of the bottom function equals 0, so we're dividing by 0. So our strategy here now is to apply some sort of algebraic simplification to cancel the term that's giving you a 0 in the denominator, which is precisely this x minus 1. That's what was turning into 0. So in our solution, before evaluating the limit, we would like to factor the top, and ideally, we'd like to factor an x minus 1 out of it, so these two terms would cancel. Let's see if that's possible. If this were to happen, the term that would have to go here would have to be a 3x, so it multiplies with the x and gives us 3x squared. And then we'd have to have, let's see, the last terms, this times that, would have to give us a minus 8. So we need a plus 8 right here. And let's see, is this a valid factoring of the numerator? Let's FOIL it back. 3x times x is 3x squared. Then 3x times minus 1 is minus 3x. Plus 8x is 5x. And 8 times minus 1 is 8. So yes, we have successfully factored the numerator. And the x minus 1s now cancel. And this limit becomes, the limit as x approaches 1 of 3x plus 8. Suddenly we have a limit that we can evaluate. Whereas up here where we started, we couldn't evaluate this limit because we were getting 0 in the denominator. Now the denominator has gone away. We've canceled it out. And the limit as x approaches 1 of this polynomial, 3x plus 8, would just be 3 times 1 plus 8, or 11. So we have our answer here. The limit equals 11. I'm going to do a slight variation on this example to drive home a point. In example 2 prime, it's almost the same problem as example 2 that we started with, except that instead of x approaching 1, x is approaching 2. Now, if you wanted to, you could factor, as we did here, to solve this problem. However, notice that as x approaches 2, the x minus 1 on the bottom, it's not turning into 0. It's turning into 2 minus 1. So for this problem, we could actually apply our limit law if we wanted to. Or we could just look at, take the limit of the top divided by the limit of the bottom. Or alternatively, just look at this as a rational function. We know that to evaluate the limit, we just plug in 2 for the x's and get 14. So in not every limit will you have to algebraically cancel. You only should algebraically cancel when you have a limit that is giving you a 0 denominator. You try to cancel that 0 denominator, and that wasn't happening here. Next, let's look at the limit as x approaches 3 of 1 over x minus 1/3 divided by x minus 3. Now, always when you're evaluating limits, your first reflex is going to be to apply a limit law. You might look at this limit and say, well, I have the limit as x approaches 3 of a function divided by another function. So applying a limit law here would be the limit as x approaches 3 of 1 over x minus a third divided by limit as x approaches 3 of x minus 3. But when we work that out, it gives us 0 divided by 0, which clearly is wrong. And you see exactly what happened that messed us up here. This limit as x approaches 3 of x minus 3 in the denominator, that equals 0. So the limit law doesn't apply in this step. We were wrong to try to apply it. So let's think about how we would solve this limit. The limit as x approaches 3 of 1 over x minus a third divided by x minus 3. I'm going to show you a trick that you should be alert for. In working out this limit, you can multiply it by 1, which will not change anything, but you can choose to multiply by 1 in a very convenient form. What we could do is multiply by 3x divided by 3x. Now the reason I've chosen 3x divided by 3x is that 3 times x is the common denominator of these two fractions. If we multiply the 3x into the top, it's going to multiply times the 1 over x to give us a 3, and multiply by the negative 1/3 to give us an x. And thereby we will simplify these fractions, and perhaps then we could get some cancellation. Let's try it. So multiplying the 3x, distributing the 3x into the difference of fractions, 3x times 1 over x is 3, 3x times a third is x, so you get 3 minus x here. And on the bottom, let's just leave it as 3x times the expression x minus 3. We're not going to distribute into the bottom because remember, we're hoping to cancel that x minus 3. So let's leave it factored. So notice that when this happens, you get a 3 minus x on top and you have an x minus 3 on the bottom. Those two things are almost the same quantity. One is just the negative of the other. In fact, we can factor out a minus 1 from the top to get the limit as x approaches 3 of negative x minus 3 divided by x minus 3 times 3x. Negative x minus 3 is 3 minus x after all. Now we get some cancellation, and we have the limit as x approaches 3 of negative 1 over 3x. And here we can apply a limit law. We get the limit as x approaches 3 of negative 1 divided by the limit as x approaches 3 of 3x, giving us negative 1 divided by 3 times 3, or negative 1/9. So there's our answer. So the moral of this story, this example, is to try multiplying by 1 in the form of an expression divided by itself that has the potential of simplifying parts of your expression. Technically, you can multiply by any expression divided by itself as long as it's not 0 divided by 0, but only certain expressions divided by themselves are going to give you traction. Here it had to be 3 times x to simplify this to 3 minus x. Choosing the right expression to pull out of thin air, as we did here, is something that you will gain from experience. You need to work a lot of these problems, and you'll start to see possibilities as you work them. You'll get to the point when you're on a test, you're working a problem like this, you'll immediately recognize what to do. Sometimes when you're first starting, it can seem a little bit formidable. But don't worry about that. Just keep working the exercises. That's the key. In example 4, we have the limit as h approaches 0 of 1 over 2 plus h quantity squared minus 1/4 divided by h. So our first try might involve taking the limit as h approaches 0 of the top divided by the limit as h approaches 0 of the bottom. And that gives us this, 1 over 2 plus 0 squared minus a fourth divided by 0, or 0 over 0, which is clearly wrong. And the problem, of course, is that you have this h in the denominator that's approaching 0, so you're getting a 0 in the denominator. So what we need to do here is to somehow cancel this h on the bottom before we work out the limit. So let's see. What could we do? We can take this limit that we're trying to evaluate, and taking a cue from the previous slide, we could multiply by an expression divided by itself, which is just multiplying by 1, so it's not going to change anything. And mimicking the idea from the previous example, a good strategy would be to multiply by 4 times 2 plus h quantity squared divided by itself, because that would knock out these fractions. Multiply by 4 times 2 plus h quantity squared divided by itself. Now let's distribute that into the numerator and also multiply the two denominators to simplify this. Working the numerator through, the 4 times 2 plus h squared times the 1 over 2 plus h squared is just a 4. And then the 4 times 2 plus h squared times the negative 1/4 is minus 2 plus h squared. Now on the bottom, we're just going to multiply these terms, h times 4 times 2 plus h squared. We're not going to FOIL anything out or multiply through on the bottom because we want to leave that h factored. We're hoping to cancel it. Now, does it cancel with something on the top? Well, let's see. We may have to FOIL out the 2 plus h squared first. So we get the limit as h goes to 0 of 4 minus 4 plus 4h plus h squared when we FOIL this out, divided by the same denominator we had in the beginning, or above. And now let's distribute this negative into the parentheses, and you get a 4 minus a 4. And those cancel out, and that negative will continue to change the 4h to a negative 4h and the h squared to a negative h. So after the 4's cancel, we get the limit as h approaches 0 of negative 4h minus h squared divided by h4 times 2 plus h quantity squared. Now, can that h cancel? Actually, yes, because we could factor an h out from the top. Doing that, we get this limit as h approaches 0 of h times negative 4 minus h, that's the h factored out here, divided by our previous denominator, and now those two h's cancel out. Now that's good because remember, the h on the bottom was precisely what was causing the problem here. It was approaching 0, and we've just canceled it out. What are we left with? The limit as h approaches 0 of negative 4 minus h over 4 times the quantity 2 plus h squared. Now looking at this, it's a rational function in a variable h. It's a polynomial on top divided by a polynomial on the bottom, where the variable is h. So we have a limit law that says we can evaluate this limit simply by plugging in h equals 0, wherever you see an h, here and here. And in so doing, we get an answer of negative 1/4. So this limit equals negative 1/4. Example 5. Evaluate the limit as x approaches 7 of the square root of, limit as z approaches 7 of the square root of z minus 7, square root of 7, divided by z minus 7. So here in our first try, we might just plug in a z equals 7 into this function, taking essentially the limit of the top divided by the limit of the bottom, and you get square root of 7 minus square root of 7 over 7 minus 7, or 0 over 0, which is clearly wrong. So of course, the problem is that the denominator, the z minus 7, is turning to 0 as z approaches 7. So we would like to cancel this z minus 7 that's turning into 0. Now I'll show you a trick that you can use when radicals are involved, and especially when you have a difference of two radicals. You can take this limit and multiply by the conjugate of the square root of z minus the square root of 7 divided by itself. And the conjugate of that expression is just that expression with the negative changed to a positive. So here we are, we're multiplying this limit by 1 in this convenient form. Now why would we do that? Well, if you FOIL out the top, you get the square root of z times the square root of z, which is the square root of z squared, plus the square root of z times the square root of 7, minus the square root of 7 times the square root of z, minus the square root of 7 times the square root of 7, which is minus square root of 7 squared. So these middle terms cancel out, and the z, square root of z squared, that's just z, and the square root of 7 squared is 7. So the top is going to simplify dramatically. And on the bottom, we just multiply these two terms in. We're not going to distribute that because we want the z minus 7 to cancel. So on the top, we're only left with the square root of z squared, which is a z, and a minus square root of 7 squared, which is a minus 7. So here we are in a situation where these two terms cancel. And we're left with, the limit as z approaches 7, of 1 over square root of z plus the square root of 7. And working out the limit of the top divided by the limit of the bottom, we get 1 over the square root of 7 plus the square root of 7, which is 1 over 2 square root of 7. So there's our answer. So be on the lookout for where you can apply this conjugate trick to limits involving differences of radicals. It very often works. I'm going to show you another way that you could evaluate this limit, a different solution. We've got the limit as z approaches 7 of the square root of z minus the square root of 7 divided by z minus 7. Now, it doesn't look like it, but the z minus 7 on the denominator, it's actually a difference of two squares. The z, let's see, z is approaching 7, so z is a positive number. That z, it's something squared. It's the square root of z squared. And the 7, it's also something squared. It's the square root of 7 squared. So we could write this limit as the limit as z approaches 7 of the square root of z minus the square root of 7 divided by the square root of z squared minus the square root of 7 squared. Now mind you, the square root of 7 squared, it's just 7. The square root of z squared, it's just z. So all we've done is we've re-expressed this limit into a slightly more convenient form where we clearly have a difference of two squares on the denominator. This squared minus that squared. So now if we factor the denominator as a difference of two squares, it's the square root of z minus the square root of 7 times the square root of z plus the square root of 7. And these two terms here cancel and simply give us the limit as z approaches 7 of 1 over square root of z plus the square root of 7. And now take the limit as z approaches 7 of the top divided by the limit as z approaches 7 of the bottom. The denominator is no longer turning into 0. It is the square root of 7 plus the square root of 7 when this z approaches 7. And that's 1 over 2 square root of 7. Of course, exactly the same answer that we got above. So of course, there are many, many different ways to solve these problems. Two valid solutions of this one shown here. In our final example, 6, we evaluate the limit as x approaches 2 of x plus the absolute value of x minus 2 divided by x minus 2 plus 1. Now, if we were to naively work this out by just putting x equals 2 into this function, we'd get 2 plus the absolute value of 2 minus 2 divided by 2 minus 2 plus 1. And the 2 plus 1 is 3. And the fraction turns into 0 divided by 0. So just plugging in x equals 2 is clearly wrong because we're getting 0 divided by 0. So we have to be somewhat more clever here. And the key to this problem is to look at this function we're taking the limit of. In particular, notice that because you have an absolute value here, the absolute value of x minus 2, this function behaves differently depending on whether x is bigger than 2 or less than 2. Because if x were bigger than 2, 2 minus x is positive, and the absolute value does nothing at all. Whereas if x is less than 2, x minus 2 is negative, and the absolute value is taking the absolute value of that negative number. It's multiplying it by negative 1. It's doing something to it. We have really a piecewise function. It's going to work out differently depending on whether x is less than 2 or greater than 2. Now I said if x is greater than 2, then the absolute value of x minus 2 is positive. So the absolute value is doing nothing. You can just drop the brackets, and you get x minus 2 divided by x minus 2, which is just 1. So this works out to be x plus 1, which is x plus 2. But if x were if x were less than 2, then x minus 2 would be negative. So the absolute value of x minus 2 would be the negative of x minus 2. Take the negative of that negative number. And the negative of x minus 2 divided by x minus 2 is negative 1. And we'd get x plus negative 1 plus 1, or simply x. So this function works out to be x if x is less than 2, and it's x plus 2 if x is greater than 2. So this indicates that the right-hand limit and the left-hand limit of this function are going to behave differently. Look at the limit as x approaches 2 from the left of our function. If x is approaching 2 from the left, x is less than 2, so this whole function is just x. And we get the limit as x approaches 2 from the left of x, which is clearly equal to 2. But if we look at the right-hand limit, the limit as x approaches 2 from the right of our function, then x is greater than 2, so our function equals x plus 2, and we have the limit as x approaches 2 from the right of x plus 2. And this limit is equal to 2 plus 2, or 4. So because the left-hand limit as x approaches 2 and the right-hand limit as x approaches 2 of this function equal different numbers, we have to conclude that the limit as x approaches 2 of x plus the absolute value of x minus 2 divided by x minus 2 plus 1 does not exist. You can see geometrically what's happening when you look at the graph of this function, x plus absolute value of x minus 2 divided by x minus 2 plus 1. For x greater than 2, the function is x plus 2. So y equals x plus 2 is a straight line with slope 1 and y-intercept 2. So slope 1 and y-intercept 2 would be this line, but we only draw that line for values of x greater than 2. Whereas if x is less than 2, our function is just y equals x. So for these values of x less than 2, we graph y equals x, which is a straight line with slope 1 and y-intercept 0. So the graph of our function looks something like this. It has a break in it. And sure enough, you can see here that as x approaches 2 from the left, f of x gets closer and closer to 2, as indicated, or as we computed here. And as x approaches 2 from the right, f of x is getting closer and closer to 4, which reinforces the 4 that we got here in the right-hand limit. So occasionally you'll have a problem like this one where you have to break it down into right or left-hand limits. It's always good to work a few examples like this. That's it for today. Our big point has been, if you are getting a zero denominator when evaluating the limit, try to cancel the expression that's creating the zero. Next time, we'll talk about limits involving trig functions. But for now, it's very important to get some practice with the kinds of limits that we work today. You'll find that you will get good at it very quickly, but that doesn't happen unless you work lots of examples and exercises. So please do that. And I'll see you next time. Goodbye.